Well, thank you, everyone. Thank you for coming. Today, I would like to talk to you about an exciting piece of software we're building at H2O that automates predictive modeling, specifically for supervised tasks. But before I do, I'll tell you a little bit about my background, specifically in Kaggle, because I think it's very relevant to what we do, and my work specifically. So hopefully you will find it interesting. So about my background, I work as a competitive data scientist at H2O AI. If you don't know the company, it specializes in building predictive modeling software, and it is a leader in the field. And the competitive element here means that I need to make certain that what the company builds is very well competitive against the best, against what's out there. So this also involves me and other people competing a lot in Kaggle and making certain that, again, it's really competitive. That's in case you were really wondering about the title. A lot of people ask me about this. I did my PhD at UCL specifically about ensemble methods. And when we say ensemble methods, we refer to combining many machine learning algorithms in order to get a better prediction for classification or regression tasks. And while competing in the Kaggle platform for 5 years, I've managed to get to #1 at some point last year. I'm actually still third. I'm not playing as much anymore. But yeah, it is a great experience, and I draw heavily for making certain we build very predictive software. And the reason is, but before I go there, I would like to talk to you about how I enter into data science, because you might find that interesting. So I came here to study. I did a master's degree in the University of Southampton. I'm originally from Greece. And after I finished that course, I started attending these entrepreneurship type of talks where different business professionals come and talk to you about how they succeeded and give you ideas about what you can do next. And there was a person, his name escapes me right now, but he described how after he finished a similar course with us, he didn't actually started working immediately, but he started going to the horse races. And he was telling us that his parents were very disappointed, obviously, that he didn't use his degree to go out there and get some money. Instead, but what he did is actually was very smart. For 2 years, he was going to the horse races. He wasn't really betting, but he was collecting data, like stuff like weather condition, who won which race, where do people bet the most. And after 2 years, he managed to build a predictive model, a simple logistic regression model to predict the winner, and it worked quite well. He started making quite good money from it. Then he sold the algorithm, made the book. The point is, the way he explained it, I was like really fascinated. It seemed like a superpower that to predict the future, and he basically made something out of nothing. Like he just was gathering data for 2 years, and he was able to build this. So I thought that was really, really impressive, and that's when I said, I need to do more of this. So I started picking up predictive modeling skills, initially with the tools that were more like statistical tools, like SPSS, SAS. But then I thought I need a bit more autonomy, so I expanded to Python and Java. And at the same time, the whole data science thing, became a thing, basically. So yeah, once you pick up more skills, you want to test them somewhere. And this is where I found Kaggle. And someone could define Kaggle as the world's biggest predictive modeling competition platform. I think this is how it started. I would say now is more than that. They call themselves the home of data science, and I personally like this title because you can do a lot more things than predictive modeling. You can get free data for various problems that could help you build better predictive models. So for whatever you do, you learn how to code, you learn how to solve different data science problems. And again, there is also the competitions part, but personally, I always advise people who work in this domain, in data, to have an account there and just be up to date, like with, spend 1 or 2 hours every week to see what's new, because it's very research driven. It has more than 1 million members right now, and is still expanding. And the way it works, at least the competition part, is that different companies will host different data science challenges for a prize. It's a way to outsource problems, basically. And either professionals in the fields, let's say data practitioners, would try to solve them. And there is also a league about this. So the more you participate, the better positions you get, the more prizes you accumulate. Similar with tennis. If someone has seen how tennis works, where you need to keep competing in tournaments, it's actually very similar. So at some point, I was able to get ranked first out of 500,000 registered members, which I think it's the biggest achievement of my life. Yeah, but I also draw a lot of learnings from it, which I'll come back later on. I just want to show you a few typical problems you'll find on Kaggle. The first is like typical tabular data set, some categorical features like is someone a homeowner, and some other numerical attributes like age, current balance. Can we predict default? If we also know other features like the income of someone. That's a typical problem. Other stuff you can do and you can learn to do is image classification tasks, like can I differentiate from a dog and a cat? And these problems are, as you may know, very solvable, but very popular in Kaggle right now. You can get extremely high accuracies, like over 99%. Other typical things is if I have some sound clips that different bird species appear, can I learn to differentiate which bird species appears in a clip? Again, it's just a matter of loading the data, transforming it into a numerical representation. Normally, we use Fourier type of features here. And then just use a machine learning algorithms to do the differentiation. That's another typical problem. Again, very solvable. You can get extremely high accuracy for this kind of problems. Other stuff that usually encounter is like text, NLP tasks, test classification tasks. So from some text, let's say I have some books written from some authors. If I get a sentence written from another book from these authors, can I find which one wrote it? And again, you can get extremely high accuracies to this problem because every person has his own identity in the way he or she writes. Or other typical things is like sentiment, particularly useful for social media to get feedback. Try to identify if a certain sentence contains something positive or something negative. And again, if you have lots of data, these problems are extremely popular, very solvable, and also very, very popular. So I just put together a few learnings of what you need in order to win in these extremely competitive tasks where 3,000 or 4,000 teams will compete for a prize. And I think it sums down, this is just my personal opinion, but it comes down to, first of all, understanding the problem you're trying to solve, understanding what kind of metric you optimize and what could be affecting this, and then go deeper into the very specifics of the problem. For example, just to give you an idea, I remember there was an insurance company that was trying to predict which policy a person would pick. But you could see that in most cases, people were renewing. So it was actually more valuable to break this into a two-stage problem. Say, will the person renew or not? If not, let's see what the person is going to pick. So I'm talking about this kind of things which are very problem-specific, and you may need to set this up a bit differently. What I have found extremely useful in Kaggle, and not only, like in my work too, is to be able to recreate an internal validation environment to test what I'm doing, basically, to test my algorithms, to test the features as I have, and see how they would perform when I'm actually going to test that model. It is important to recreate that testing environment internally, because then you can try all sorts of things and you can really see what is working. You can almost convert this into a constant hypothesis testing approach. I add one feature. Is there uplift? Yes. I keep it in. No. I discard it. I try something else. If I have a reliable testing method, then I can try all possible transformations, all different permutations in my data, and be confident about the result. Obviously, the other elements that a lot of uplift comes from is how you handle the data. This involves how you treat missing values, how you treat numerical features, how you treat categorical features, how you create new features and you explore interactions. These kind of things are really important, and a lot of value is derived from these processes. Then you need to know the problem-specific things. For example, in image classification, unless you try convolutional neural networks, you are not probably going to score very high. And again, every problem has most probably its own favorite algorithm or best way to solve it. So you need to know these things to be able to score well. And similarly, access to the right tools. This doesn't only extend to software, but also to hardware. Obviously, the better hardware you have, the more things you're going to experiment and try. And eventually, you can get better scores. Naturally, the hours you put in. And I remember on that stretch, when I got first in Kaggle, I was spending something like 60 hours per week on top of anything else I was doing, like on top of my day job. So it was quite exhaustive, and other people more talented, less time. But this is, you generally need to dedicate time to get better results. Collaboration is very important, and I still think data science is a team sport. Because when you have more than one person, basically, you can divide the workspace. Someone can say, I will focus on feature engineering. Someone else will say, I'll focus on building a good deep learning model. And generally, you can cover more ground. Also, every person seizes the problem slightly differently. And this leads to solutions which are more diverse. And when combined together, they yield more value, more unique information, let's say. So I think that part is very important. Obviously, you build, with experience, I think over time, you know where to optimize your time more. Also, you know what stuff have worked well in the past for similar problems. And again, you can be quicker. And the last part is, normally there is a phase in the end of every competition where everybody has created different models, different predictions, and then you need to find the best way to combine them. This is what we call ensembling, and in itself, it's a different part. It requires its own setup. So that's generally, from my experience, what you need to, in order to win, like on a very high level. The good thing is that we have found out that a lot of these things can be automated, and can be automated quite well. And this is where H2O driverless AI comes in, which tries to do exactly that. So for supervised problems, initially at least, tries to, where you have a data set, you have like a target variable, it tries, and a few other parameters like a metric, how much resources I have available. It tries to optimize so that you get the best score possible given some constraints. I think a nice way to describe it is that it is an AI that creates an AI, because essentially is a tool heavily based on machine learning that generates machine learning models. So it sounds a bit meta, but I think this is a good way to define it. And it includes several steps from importing the data, creating features, selecting algorithms, doing feature selections, and obviously making predictions and doing assembling, the combination of models as described before. And I would like to go through a few of these steps and how we do it on a high level. You will find out, especially if you go to the website, that there is a lot of clarity on how we do these things. But you need to find the specific section that talks about each one of these processes, like the feature engineering and the modeling. So yeah, forgive me if I don't go too much in detail today. You can always find all the information online about the specific sections. So going on to the feature, and before I go to the feature engineering, I just need to tell you that this is a software that is built by, I would say, some very strong people in the field, either data scientists, Kaggle grandmasters, which is a title given to only 100 participants in Kaggle, those that have won the most challenges. And obviously a lot of engineers and academics, just a few names. Matthias used to be the first in Kaggle in the European Union at some point. Sudulai was first in India. Matt, I'm not sure if people use data table in R. He's the main author. It's very popular. And many other people, you can find them out, but everyone is I just want to say it's a very diverse group with different skills, with all leaders in their field. And moving on, how do we do the feature engineering when we import the data? And we start with categorical variables, and I'm just giving a very naive example here. Let's say we have a categorical feature called animal that takes different values like dog, cat, and fish. So we explore different transformations. We try to find the ones that will give the best possible results given some objective. And we will try stuff like frequency transformation. So let's just try to replace every distinct category by how popular it is, like how many times it appears in the data. So this kind of representation tends to work very well for some machine learning problems. Other things we will try is just what we call label encoding. So just sort alphabetically, assign an index. And again, in some problems, this tends to work quite well. In some others, not so much. Other ways to do this is to create dummy variables. I believe many people may already know this. So convert each distinct category into a binary column, basically. And we can try other stuff too, which fall into target encoding. So assuming we have a target variable, we try to predict which is cost. So just calculating the average cost of each of the distinct values, each of the categories, we can just replace with these values, and then we have a variable that is related already with the target. Obviously, we don't do it exactly like that because we want to avoid overfitting, but that's the general idea. So I give you some examples of the kind of different transformations we are looking at when we import a data set. Similarly, we transform numerical features. So we have something like age. Something we often try is just try to bin this, try to find the best bins and transform this into a categorical variable. And again, this representation helps in multiple ways. It caps outliers. And it also makes it easy to combine with other categorical features. We find different ways to handle missing values. We can replace with something like the mid, or we can take on the categorical approach and just treat it as a different category. Again, the best transformation is found through a hypothesis testing type of approach. Keep trying, keep iterating, try to find the transformation that will yield the best results. We also explore interactions. So we have age and income. We can take their multiplication or their sum. We can combine categorical features, like simply by creating a new categorical feature. For example, dog and brown, dog underscore brown. Or we can have a numerical and categorical, and we will use the same approach as before, the target encoding, just replace with the average of that of the continuous feature. And we can do other things too, like first convert age into a categorical with the bins you've shown before, and then actually go with the middle approach. Just different ways we try to look at the data, and we can actually go out up to 6 and 7 way interactions. So 6 and 7 features together, we have found that this, in certain problems, can yield uplift. Other things we can handle is text. Again, the recipes are not very complex. You have a sentence, you create a vocabulary, and then you try to see how many of these words are triggered out of all possible words in a single sentence. So if a sentence has the dog too many times, what does it mean? Does it mean the owner is a good person or not? I say yes. And then we apply other sort of techniques to try to make this matrix of words, which can be quite big, smaller. We use dimensionality reduction techniques like singular value decomposition or word2vec. We also, this is an upcoming feature, but I should tell you that we are also looking into time series. When we say time series, is when there are strong temporal elements in your data. So when what you try to predict is strongly affected by what happened, let's say, in the past. So if I know the sales yesterday, can I predict the sales tomorrow? So about this type of problems. And again, we do different feature engineering here. If you have something like a date, you can extract the day elements, like day, month, year, weekday. Or you can create lag variables. Let's say if you have something like sales, you can see what happened 1 day ago or 2 days ago. And then obviously you have other aggregated type of measures like moving averages, exponential smoothing, and other aggregate type of features. At this point, we rely a lot on XGBoost, not only, but for a start, we rely a lot on XGBoost or extreme gradient boosting. It is an algorithm that has actually won many machine learning challenges. It is very efficient. You can run in parallel, both on GPU and CPU, and particularly the GPU implementation is very good. It's extremely fast. Hence, we really like it. It's very parameterized, and you can easily control overfitting and underfitting with careful tuning. It supports many loss functions and can be used for regression and classification. We do what we call hyperparameter tuning. That's another thing that can be automated, but we try to keep it simple in order to save time, yet achieve generally good results. Things we look at, because this is basically a tree-based algorithm, we try to optimize for maximum depth, like how deep should the tree be, each one of the trees in XGBoost, and different ways to expand the trees based on levels or based on loss, and then number of trees, like how complex should our model be? Should it be a big ensemble or a small ensemble? Again, depending on different parameters the user sets, this can take different values. Also depends how high accuracy the user wants to achieve and how much time he has available. And the validation part is really important. In something like time series, we normally have the data sorted based on time, and we will obviously have past predicting future. But for many other tasks, we normally rely on k-fold cross-validation. And we like this approach because it's also very suitable for the ensembling I mentioned before. It's very suitable for combining different algorithms, because what you can do is first you chunk your data into different parts. Here are, say, k parts, and k equals 4. And you use one part to train a model and the other part to make predictions. And then you save these predictions in the corresponding parts, so the same rows that refer to the blue part. And you keep doing this, basically, with different parts. So this time, I'm predicting the red part and put the blue back into my training. And now I'm going to score the red part. And I will keep doing this until I score all my data in this holdout fashion. And now we have predictions for our training data, all produced as this holdout approach. So they're fairly unbiased. And now that we have these predictions, we can actually generate many this way, different algorithms and slightly different features, and put them together, and now fit a new model on these predictions. We use something called linear blending at this point. It's not very complicated for now. It just tries to find the best linear ways to combine these algorithms, these predictions we generate through the previous procedure. So essentially the best weights. Later it will be more sophisticated. This is like that for quickness. So yeah, current recipes include regression, classification, text, and time series is upcoming. Obviously more will come in. Roughly to explain to you what is the process of driverless AI. So you have some input data. You imagine like an Excel spreadsheet, right? Some data. You have a target column, something you try to predict. Could be binary if someone will default. Could be regression, predict me sales or income or stock prices. And then you select an objective function, like I want to minimize error or maximize accuracy of prediction. And then you allocate some resources. Say I want to put some, I have 2 GPUs I want to use, or I have some CPUs I want to use. Then driverless starts running. And when it's finished, it gives you different outputs. The outputs could be predictions, but you could also get model interpretability. So why the model gives you predictions the way it does. Why, let's say, a customer has been scored in a specific way. So it gives you a lot of reasoning codes for, and try to help you understand why the model gave the prediction it did. I think this module is very interesting. You should, but there's more details online. Naturally, you can get inside, and what I really like is that you can also export all the feature engineering that is being done. So you can see the actual features that were created, which I mentioned before. And you can learn from it. You can use it in other models if you think you have other algorithms. You can just export these data sets with the transform features and try it on your own algorithms. Yeah, these two similarly. And this is what the output would look like after a model has finished, basically. So on the left, some details about how many rows it has, how many columns, how many unique values the target variable had. Then you have some after model options, like score another data set, transform another data set, download predictions, downloads like a scoring pipeline that will help you to score with Python, like you no longer need driverless. Here you can see the best features created, and if you hover, you can see an explanation about what exactly they are and the ranking. And here you can see the loss over time. Here we were optimizing for log loss, so the smaller the better. And you can see, through the different iterations of the model how this was decreasing. And especially you can see a small jump downwards at the end. And this is the impact of ensemble we always do in the end. So in the end, we just combine many different algorithms after we found the best possible features. And you normally see that kind of boost in the end in your predictions. And now I would like to show you a demo. I recorded my screen because I thought that was best. About how this works is not much, it's 3 minutes. In a specific Kaggle competition, which was quite popular, it had around 3,000 teams, 130 anonymized columns. It was an insurance type of problem where you had to predict, given some anonymized customer characteristic and policy characteristic, should we accelerate approval of a claim or not, obviously to save costs. So driverless AI could score top 16 out of 3,000 teams within an hour. The impressive thing is that it took my team 3 weeks to get there the first time I tried it. And we finished third eventually, but we put a lot of effort. So it's amazing that you can do this in 1 hour. So this is roughly how it works. You select a data set. That's the screen. Here it trains CSV. It loads it, and it gives you some details, how many rows, how many columns. Then you select the test data set. I exclude the ID column. I select my target column. And then I say how much resources I want to allocate. So I want to go for 9 accuracy and 7 time. Again, this controls how deep this goes. I select I want to minimize log loss. And I begin my experiment. And then the experiment will start running. What it does first is it streams through the data and tries to initially optimize some. It runs a very basic model, an XGBoost model in this case, in order to get an initial baseline on those base features. It doesn't really do something very, very smart initially. It tries to give you this baseline. It only tries to optimize some of the XGBoost parameters, mostly the maximum depth. And then you start getting your first model. You get a first error, which is sort of your baseline, which in most cases is actually quite good. It's normally already a good score. And on the right-hand side, you can see dynamically different curves that shows performance. For example, you can see the area under the rock curves. You can see the hardware usage over time and the ranking of the best features. So which is the middle. As you see, this keeps changing over time through different iterations. The interesting thing is while it runs, I can now forget this and go and visualize a bit the data. The interesting thing about the visualization here is that it will only focus on parts which are interesting. For example, here shows you some distributions. You can see some outliers, and you can look into this case specifically. It's retrieved as an Excel sort of line. And you can see, why certain features have extreme values. You can see other interesting correlations between some of the features, which they may also give you an idea whether you want to handle them differently if you want, like on your own. Here you can see some variables are actually very correlated. And it's really different options, and this is an area which is heavily expanding right now. So I would say this is still a very simple version of it. Then we can go back, we can continue with the experiment. What I'm going to do next is I'm going to fast forward into about 1 minute to see like the whole procedures. We are 12 minutes in. Ranking of features keeps changing. Loss keeps dropping over time, but we are essentially plateauing. Like there is no that much to get after a while. Also, you may see that the AUC decreases at some point, although log loss becomes better, smaller, and that's because the model focuses on log loss and not on AUC. Still, it's interesting to see the two. And in around 1 hour, so 15 minutes from now, is going to reach sort of the best point. And then now is actually going through this ensemble phase. So at this point, it's now combining many different machine learning models. And remember that score 4426, it reduced it a bit more through combining different models. So this finished, and I selected this interpretability option, which basically what it does is it takes the prediction and it fits new models, making these predictions as target, because this is a neat way to try to predict the model. And you can control the complexity, you can control how deep can be that, we call it the surrogate model, that predicts your score, and it gives you back intuition about why your model scored the way it did. And I don't want to spend more time on this because there are specific videos online only about this section, and also the person describing them is much more qualified to talk to you about this. But it's a very interesting area, this interpretability, and we do a lot of work to give you reporting and feedback about why the model gave the predictions it did, just for the sake of showing this is where that model finished, 16 out of 3,000 teams. Driverless has received many awards this year, and H2O has received many awards in general, including the Gartner Award, which was a leader in innovation. You can get a free trial there for is 21 days, and you can give it a shot. Also, you can find all these videos I mentioned, which focus on different areas: feature engineering, the ensembling, the model interpretability. You can find them online, and you will find out that there is a lot of clarity again about how we do these things. And yeah, and that was it. Thank you very much for your time. Hopefully I didn't bore you, and happy to take any questions.
Okay, we've got a few minutes for questions. Okay, gentleman over here.
Hi, it was a really... Can you hear me?
I'll just maybe go there.
Hello? Yeah, that's all right? Okay. It's an interesting talk. So I've used H2O for a while now. I've used AutoML.
Yes.
How different is AutoML from Driverless AI?
Yeah, AutoML is different because AutoML doesn't focus on feature engineering. So it almost excludes this part. So it's what it does is it imports the data. It will select a default transformation. It will not try to find the best feature engineering transformation, but it will run multiple different and diverse machine learning algorithms and will try to find the best way to combine them. So this part is consistent in both software. The difference is that the feature engineering part, which is a strong difference. I mean, a lot of uplift comes from there. Yeah. But in the future, I think even this part will be improved. Yeah.
Thank you. Have you thought of using unstructured data for features, like if images or emails were features?
So images not yet. I mean, in the future. I mean, fairly a structure is the text, right? So text we can handle pretty well, as I mentioned. Images not yet, but in the future this will be added. Yeah.
How do you make sure that you are not overfitting the training set by running all this optimization and optimizing the cross-validation score?
Yeah, we rely a lot on our cross-validation, and actually we have a blog about how exactly we prevent overfitting. We do a lot of checks to see how consistent. If you provide a test data set, for example, we do a lot of checks to make certain that the training data is consistent with the test data. You know, like the distributions are not far off, that they don't span on different values. And then we search a lot if there are temporal elements in the data, if there is a specific ordering association with the target variable. Like if you have a date, we try to make certain that we always use past to validate future. But generally, we rely a lot on trying to create a reliable validation environment. Like if you have date, always past predict future. If your data seems to be generally random, drawn randomly, then we rely on k-fold cross-validation. And we do a lot of consistency check between the train and the test data to see how similar they are. I mean, yeah, that's. I mean, there still might be cases which, you know, predictions might be off, right? But in general, this ensures that you're getting quite close, quite safely in good predictions.
Okay, we've got time for one more.
Are there any particular considerations that you'd make for determining a ratio between the volume of training data and validation data?
This is basically control based on the parameters you set in the beginning about accuracy and speed. So yeah, I mean, for speed, we will do less, for example, faults, but this is more resistance against overfitting. But if you really want to have accuracy and you have very big data, and then big is is still a bit vague, like how much is big, depends on the problem. Then you can go for maximum accuracy, which means that you can do a lot of cross validations, and you can feel confident that each fault has enough data to give me representative score predictions.
Marius, thank you. Another round of applause for Marius, please.
Thank you.
Okay, guys, I probably